This is SpaceTime, Series 21, Episode 92. Coming up on SpaceTime. A super-Earth discovered orbiting one of our nearest neighbouring star systems. A new theory which could help explain the absence of antimatter. And a giant impact crater discovered hiding beneath the Greenland ice sheet. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered an exoplanet orbiting Barnard star, the second nearest star system to the Sun. A report in the journal Nature claims spectroscopic measurements using the giant 10-metre Keck Observatory upon Mauna Kea in Hawaii detected what appears to be a planet about 3.2 times the mass of Earth orbiting Barnard star every 233 Earth days. The planet's been provisionally named Barnard Star B, with the catalogue number GJ699b. Barnard star's a spectral Type M red dwarf, located just 6 light-years from Earth, with only the Alpha Centauri triple star system at 4.3 light-years distant being closer. Its proximity to Earth has made the system a long-time target for planet hunters. Barnard star is among the nearby red dwarfs that represents an ideal target in the search for exoplanets that could someday actually be reached by future interstellar spacecraft. The newly discovered planetary candidate's orbit would place it well beyond the snow line in the Barnard star system, meaning volatiles such as water, ammonia, methane, and carbon dioxide would form as ice grains on this frozen world. One of the study's authors, Cristina Rodriguez Lopez, from Spain's Institute of Astrophysics in Andalusia, says the discovery means a big boost in the continuing search for exoplanets around our closest stellar neighbours, in the hope that eventually scientists will come upon one planet with exactly the right conditions for life. She says in the absence of an atmosphere, the planet's temperature is likely to be somewhere around minus 150 degrees Celsius, which makes it unlikely the planet can support liquid water on its surface, a prerequisite for life as we know it. However, its characteristics will make it an excellent target for direct imaging using the next generation of telescopic instruments. Smaller, cooler and older than our Sun, Barnard star is among the least active red dwarfs known. And that's a good thing, because active red dwarfs, and a lot of them are considered far too violent and hostile to host planets that could support life. Red dwarfs make up more than 70% of all the stars in the Milky Way galaxy, and they're the longest living stars as well. In fact, no red dwarf that has ever existed throughout the age of the universe has yet died of old age. Although it's extremely close, being a red dwarf, Barnard star is still too faint to be seen with the unaided eye. Astronomers were able to detect the planet orbiting Barnard star using the radial velocity method in order to measure the host star's subtle backwards and forwards wobble caused by the gravitational tug of the orbiting planet. The problem is, detectable signals of a wobble from an Earth-sized planet tugging on their host star is incredibly faint and largely swamped by the noise generated simply by the boiling surface activity of the star itself. So astronomers followed Barnard star for some 16 long years using the Keck telescopes. And by 2013, they had amassed some 260 radial velocities of the star. This long-running Keck planetary search program gave the authors the years of data they needed to gather in order to get enough precision radial velocity readings to begin to sense the presence of a planet in orbit around the star. The authors then combined this Keck data with additional observations from the European Southern Observatory's Very Large Telescope, or VLT, in Chile. And this allowed them to see the first real hints of what seemed to be a 230 Earth-day periodicity in the radial velocity data, indicative of a possible Earth-sized planet. At that time, however, the signals were still far too weak for astronomers to claim it as significant and publish their findings. So the authors then added an additional 45 radial velocity measurements from the Lick Observatory, 39 velocities from the Magellan 2 telescope, and additional new raw data from the VLT. In each case, this additional data helped make the roughly 230-day signal grow stronger and more significant. The final push came when the authors undertook an intensive observing campaign in 2016 and 2017, aimed at confirming the suspected planet using a new planet-hunting spectrograph at the Calais Alto Observatory in Spain. And the additional data strongly confirmed the signal, removing any lingering doubt about the reality of this planet. A clear signal with a period of 233 Earth days showed Barnard star approaching and moving away from Earth at about 1.2 meters per second. And this annual rhythmic motion can best be explained by an orbiting planet about 3.2 times the mass of Earth. You're listening to SpaceTime. I'm Stuart Gary. Now, speaking of planet hunting, a new high-precision spectrograph has been launched in Australia to try and detect relatively tiny Earth-like planets orbiting Sun-like stars. The groundbreaking $3.8 million instrument known as Valachi has been built for the 4-metre Anglo-Australian telescope at the Siding Spring Observatory in far western New South Wales. One of the scientists behind the project, Professor Chris Tenney from the University of New South Wales, says Valachi will allow astronomers to detect incredibly tiny wobbles in host stars caused by the gravitational pull of Earth-mass planets as they orbit around the star. Previously, this Doppler shift method focused primarily on hot Jupiters, gas giants in very close orbits around their host stars. Tenney says searching for Earth-sized worlds is important because it's on these small, rocky and potentially habitable planets that astronomers will one day search for signs of life. Valachi is being built in 3 phases. The first, Valachi Rosa, will detect planets orbiting small, faint red dwarf stars. These stars are so cool that any potentially habitable planet must orbit relatively close to the star in order to receive enough heat to maintain liquid water on its surface, an essential ingredient for life. This makes the velocity wobble for these planet-hosting stars easier to detect. And Valachi Rosa, focusing on lighter red wavelengths, can measure masses for planets down to the size of the Earth. The launch of Valachi comes just months after NASA's latest Earth-orbiting planet-hunting telescope, TESS, began its own survey of the sky looking for planets using a different technique known as the transit method. The transit method involves looking for a tiny dip in light coming from a star caused by an orbiting planet passing in front of the star as seen from TESS's point of view, in the process eclipsing or blocking out some of that light. In its first month of data, TESS has already uncovered some 75 planetary candidates. And so a global astronomical race is now on to try and measure the masses of these planetary candidates in order to determine whether they're terrestrial Earth-like worlds, ice giants such as Neptune and Uranus, or gas giants like Saturn and Jupiter. Tenney says Valachi is just one of a handful of instruments in the Southern Hemisphere capable of transforming these candidates into confirmed planets with measured masses. And right now it's the only one working at the red wavelength ideal for observing these faint red M-dwarf planetary hosts. In fact, on its first night of operation, Valachi targeted an M-dwarf that TESS had found to host a planet just 1.4 times the size of the Earth, which is orbiting its host star every 0.46 Earth days. Tenney says this is exactly the type of object Valachi was built for. He reminds us that science's understanding of how life gets started remains fairly minimal. In fact, the only place known where life's got started is Earth, a small rocky planet orbiting in the habitable zone of a yellow dwarf star.
Valachi is our new planet-hunting spectrograph for the Anglo-Australian telescope up outside Coonabarabran. We've been hunting for planets up there for many years using an instrument called UCCLES that wasn't really designed for that particular job, and it did sterling work. We found more than 40 planets with it over the course of almost 2 decades, but it was showing its age, and so about 5 years ago I started making plans to build a new spectrograph. And finally, the first version of that has gone into operation. It's called Valachi Rosso because it's a red-sensitive spectrograph that is ultra-stabilized for trying to see very small planets around red M-dwarf stars.
And why red M-dwarf stars? What makes these great targets?
The reason that we particularly wanted to look at M-dwarfs is because these are small stars, smaller in mass than our sun, around about sort of 1/5 to 1/3 the mass of our sun. And that means that they're very low luminosity. And that also means that if you want to be at just the right Goldilocks distance from the star in order to have water be potentially liquid on your surface, then you have to orbit much closer to the star. And if you orbit close to these stars, the periods are shorter and the Doppler wobbles that Valachi is looking for are larger, and so everything gets easier to try and detect small, potentially habitable planets if you look around these low luminosity M-dwarf stars.
Of course, the problem with red dwarfs is that they tend to have lots of stellar flares, the sorts of things which can irradiate anything that's too close to them.
Well, you raise an interesting point. One of the reasons, though, that we get to see stellar flares and indeed X-ray activity on M-dwarfs so often is because the stars themselves are so dim. So if you saw the sorts of flares that take place on an M-dwarf star happening on a solar-type star, you'd barely notice them because the amount of flux coming from the invisible light from the photosphere of the star is so enormous. So yes, they do have these relatively large levels of magnetic activity and X-ray activity, but it's not obvious that that's enough to either stop life from getting formed or to eliminate life if it gets started. We know that our sun was much more active when it first formed, and we know that life managed to get started almost 4 billion years ago. So something like 500 million years or less after the sun first formed, and our sun would itself have done quite a lot of flaring and been quite active at that time. So it's not obvious that those are things that make life, that are inimical to life. The other thing is that we believe that life got started underwater, and X-rays and ultraviolet flux don't penetrate water to any great depth. And so if you're underwater when your life gets started, and indeed if you stay underwater all the time, then you may not give a damn about whether your star is flaring or active. To be honest with you, we really don't know. We don't know how life got started in our own solar system, really in any great detail at all. About all we can do is go and look for systems that we think might be like what our solar system was like when it got started and suck it and see whether we can find potentially habitable planets so that in 10 or 20 years' time we can point space telescopes like the James Webb Space Telescope, which NASA is going to launch in a few years' time, to see if you can see signatures of biological activity.
What sort of signatures are you looking for?
They will search for things like ozone. Methane is not really a source of biological activity. As it turns out, methane is really common in the universe. Jupiter is full of the stuff. Every sort of, star that's low enough in mass or brown dwarf has got tons of methane. Gas giant planets are full of methane. It's not really a biosignature. What you want to see is the signatures of things that can only come from biological activity. So molecular oxygen is a good thing that we think that should not really exist very much without life. We don't believe there was much molecular oxygen in our Earth's atmosphere at all before life created most of it. And ozone is then a byproduct that you get high in the photosphere of a system that's got molecular oxygen. You could look for the sorts of broad band signatures that you might expect from having chlorophyll, from having complex molecules like chlorophyll that absorb lots of visible light in very specific bands. I mean, the first obvious thing you do for is just try to look for signatures of water in an atmosphere that's thin enough to look like the Earth and not so thick that it looks like a big, heavy atmosphere like Neptune or Uranus. So there are lots of things that people will try to look for. Our job at the moment is just to try and understand how common small rocky planets that can maybe host water are so that we can try to understand how those planets formed.
Of course, we have one right next door. The nearest exoplanet to our solar system would be the one orbiting Proxima Centauri, and that's a red dwarf.
Proxima Cen b does indeed orbit a red dwarf. It's certainly a small planet, and I can bet you that when JWST does go up, it will get looked at. My interest is actually more in trying to understand how common those planets are. Do small rocky planets that can potentially host water exist around 1% of stars, or 50% of stars, or 0.1% of stars, or 0.01% of stars? We want to try and understand just how common those sorts of planets are out there in the universe.
You'll be working working with NASA's planet hunting test space telescope. As part of that test, will sort of pick up stars that look like they may have planets orbiting around them, and then you'll point your new spectrograph at them to pin that down.
Yes, so in an almost unique example of non-Northern Hemisphere chauvinism, TESS is doing an all-sky survey to look for planets that show transits in the southern hemisphere first. So it looks for the little dimming that you see as planets go across the face of their star along our line of sight. And it's actually surveying the whole sky, and it's doing it for stars very much brighter than the Kepler mission did in the Northern Hemisphere. And that means that when TESS finds these transiting planets, we can actually go and use our 4-meter telescope to try and do these Doppler wobble observations. And they're important because a transit observation only tells you about the size of the planet relative to the size of the star. And a Doppler observation, looking for the wobble of the star going backwards and forwards as the planet goes around it, tells you the mass of the planet relative to the mass of the star. And those two things together tell you what the density of the planet is. So that can help you distinguish between a rocky planet or a water world or an ice giant planet, and actually try to start to narrow down the actual detailed properties of those planets.
Tell me about first light from the new instrument.
So first light for a new instrument's an interesting process. You usually pick a nice bright star to look at, and in this case we looked at the bright star that everybody looks at when they're doing planet search programs, which is Tau Ceti. And so we pointed our spectrograph at it and got the spectrograph focused, and then took some science observations, and then had a little bit of a quiet celebration before we got back on sky to then look at LHS 3844, and got busy for the next 10 nights observing solidly on new science targets.
Valachi Rosa isn't the only spectrograph you guys are working on. There's going to be extensions to that, aren't there?
Yes, so the instrument in its first incarnation has a wavelength range that's optimized for red wavelengths, specifically for looking at M-dwarf stars. But we have funding to put in 2 more cameras into the same instrument, Veloce Verde and Azzurro, and so they will give us complete coverage when they're all installed in one shot, going from blue wavelengths all the way through to the infrared, and then give us an even more powerful facility for doing these sorts of Doppler exoplanet observations.
That's Professor Chris Tinney, a planet-hunting astronomer with the University of New South Wales. And this is Space Time. I'm Stuart Gary. According to the standard model of particle physics, the foundation stone upon which science's current understanding of the universe is based, equal amounts of matter and antimatter were produced when the universe burst into existence 13.8 billion years ago in an event now commonly referred to as the Big Bang. Physics tells us there's almost no difference between matter and antimatter other than charge. And we know from laboratory testing that when matter and antimatter come into contact, they annihilate each other, producing high-intensity gamma radiation. Now, all this begs the question, if equal amounts of matter and antimatter were produced in the Big Bang, why didn't the universe simply annihilate itself in a flash of purple light as soon as it came into being? And for that matter, why do we live in a universe filled with matter rather than antimatter? There's an abundance of evidence that shows that the observable universe is made up only of matter. If there were any large pockets of antimatter out there, it would have annihilated almost as soon as it came into contact with nearby matter to produce very highly detectable, high-intensity gamma radiation. And this has not been observed. Therefore, figuring out how the universe remained in existence, and for that matter, why it contains an abundance of matter rather than antimatter, are some of the biggest questions currently facing particle physics. And when you think about it, they're also some of the biggest questions facing science as a whole. Because of this and other gaps in the standard model, such as the existence of dark energy and dark matter, neither of which are accounted for, physicists are considering ideas which could add a few extra particles in ways that may help solve the problem. And one of these hypotheses is called the 2 Higgs doublet model, which despite its name actually adds 4 extra particles to the current 17 we know of. And the good thing about this model is that it can be moulded to agree with all particle physics observations made so far, including ones now coming from the Large Hadron Collider at CERN. But it was still unclear whether this model could also be moulded to solve the problem of the matter-antimatter imbalance. Now, scientists from the University of Helsinki have decided to tackle this problem. Their hypothesis, reported in the journal Physical Review Letters, suggested about 10 picoseconds after the Big Bang, that's a really short space of time by the way, and right about the time the Higgs boson was turning on, the universe was still a hot plasma of particles. And nothing unusual yet. This is what the standard model of cosmology tells us. But this is where it gets interesting. One of the study's authors, Dr. David Weir, says a technique called dimensional reduction allowed his team to replace the theory which describes this hot plasma with a simpler quantum theory with a set of rules that all the particles follow. Following these rules, he says it turns out that the heavier, slower moving particles don't matter very much when these new rules are imposed. And so we end up with a much less complicated theory. And this theory can then be studied with computer simulations which provide a clear picture of what happened. In particular, they tell scientists how violently out of equilibrium the universe was when the Higgs boson first turned on. And this is important for determining whether there was scope for producing the matter-antimatter asymmetry at this time in the history of the universe using the two Higgs doublet model. Weir says his team's results showed that it is indeed possible to explain the absence of antimatter and yet still remain in agreement with existing observations. Importantly, by making use of dimensional reduction, the new approach was completely independent of any previous work in this model. Now, if the Higgs boson did turn on in such a violent way, it would have left echoes. As the bubbles of this new phase of the universe nucleated much like clouds and then expanded until the universe was like a completely overcast sky, the collisions between these bubbles would have produced lots of gravitational waves. And this gives them a way to one day test their hypothesis. So the authors are now gearing up to look for these gravitational waves through missions such as the European Space Agency's LISA project, which will place a giant gravitational wave interferometer into space in order to measure dimensional changes in the fabric of space-time, as gravitational waves cause space-time to stretch and contract as they pass through it. I'm Stuart Gary. You're listening to SpaceTime. Scientists have discovered a large meteorite or asteroid impact crater hiding beneath a kilometre of ice in northwestern Greenland. A report in the journal Science Advances claims the crater, the first of any size found under the Greenland ice sheet, is more than 30 kilometres wide and over 300 metres deep, making it one of the 25 largest known impact craters on Earth. The first hints of the crater were detected by NASA's Operation Icebridge, which uses airborne ice-penetrating radar to track changes in polar ice due to the effects of climate change. Scientists from the University of Copenhagen who were studying the data noticed an enormous, previously unexamined circular depression under Hiawatha Glacier, sitting at the very edge of the Greenland ice sheet in 2015. Using satellite imagery from the moderate-resolution imaging spectroradiometer instrument on NASA's Terra and Aqua satellites, researchers also examined the surface of the ice in the Hiawatha Glacier region, finding evidence of a circular pattern in the ice surface that matches the one observed in the bed topography map. To confirm their suspicions, the authors sent another research plane over the glacier in 2016 to conduct a dense focused radar survey. The survey imaged the depression in stunning detail, clearly identifying a distinctly circular rim, a central peak or uplift, disturbed and undisturbed ice layering regions, and basal deposits. Then, during the summers of 2016 and 2017, the researchers returned to Hiawatha Glacier to map the tectonic structures in the rock near the foot of the glacier and collect samples of sediments washed out from the depression through a meltwater channel. One of the study's authors, Associate Professor Nicolaj Larsen from Aarhus University in Denmark, says some of the quartz sand coming from the crater had planar deformation features which are indicative of a violent impact, conclusive evidence that the depression beneath Hiawatha Glacier was a meteorite crater. The authors suggest the crater formed less than 3 million years ago when an iron meteorite around a kilometre wide slammed into northwestern Greenland. Over the ensuing millions of years, the resulting depression was covered by ice. Interestingly, the crater is exceptionally well preserved, which is surprising because glacier ice is usually an incredibly efficient erosive agent that would have quickly removed any traces of the impact. In fact, the crater's condition indicates the impact may even occur towards the end of the last ice age, which would place the resulting crater among the youngest on the planet. There have been lots of studies to show that large impacts can profoundly affect Earth's climate, with major consequences for life on Earth at the time. Just ask any of the dinosaurs. The authors' plan now is to continue their work in this area, addressing the remaining key questions on exactly when and how the meteorite impact at Hiawatha Glacier affected the planet. I'm Stuart Gary. You're listening to Space Time. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study has demonstrated how the continued extinction of plant and animal species due to extreme environmental change increases the risk of an extinction domino effect which could annihilate all life on Earth. The findings, published in the journal Scientific Reports, shows how this would be the worst-case scenario for what scientists call co-extinctions, where one organism dies out because it depends on another doomed species. A good example would be a plant's flower being pollinated by only one species of bee, so if the bee becomes extinct, so too will the plant. Researchers from Adelaide's Flinders University simulated 2,000 virtual Earths linking animal and plant species. Using sophisticated modelling, they subjected their virtual Earths to catastrophic environmental changes, such as global warming, which ultimately annihilated all life. Because all species are connected in a web of life, the study clearly demonstrated how even the most tolerant species ultimately succumbed to extinction when the less tolerant species on which they depend disappeared. The International Committee for Weights and Measures meeting has come together for an historic vote to redefine the kilogram. Officials from more than 60 nations are meeting at Versailles for the landmark decision. The redefinition of the International System of Units, more commonly known as the metric system, means that from the 20th of May 2019, all metric units will be defined in terms of fundamental constants of nature. The most significant change will be the end of the international prototype of the kilogram, or the Big K, a cylinder of platinum iridium stored in a vault in France. Big K has served science and technology for nearly 130 years. But it's past its use-by date, and redefining the kilogram removes the reliance on a physical object that could be unstable. The move follows the redefinition of the second back in 1967. That provided the basis for technologies that have transformed communications across the globe, from GPS through to the internet. A new study has found that Neanderthals and early modern humans both experienced similar levels of head trauma. The findings, reported in the journal Nature, challenge the stereotype that Neanderthals lived more violent lives than their Homo sapien counterparts. This stereotype came about because researchers tend to compare Neanderthals to present-day cases, which involve injuries usually only common among rodeo riders, and not the sort of injuries suffered by Homo sapiens who lived at the same time as Neanderthals. So researchers compared 800 samples spanning 80,000 to 20,000 years ago from the largest fossil database currently available. They found there was no difference in head trauma rates between Neanderthals and Upper Paleolithic modern humans. And interestingly, males from both groups were far more likely to have been hit in the head than females, a situation which one would suggest hasn't really changed much since. A new study suggests a low-carb diet may help people maintain weight loss. A report in the British Medical Journal found that when people lose weight, their body adapts by slowing metabolism and burning fewer calories, and this often leads to weight regain. Researchers wanted to see if dietary composition could change this, so they put 164 adults who had recently lost 10% of their body weight on either a high, moderate or low-carb diet for 20 weeks. Over this time, energy expenditure was significantly higher in those on the low-carb diet compared to the high-carb diet, and hormones involved in energy balance also improved. Without changing calorie intake, the increased energy expenditure could translate to around 10 kilograms in weight loss over 3 years. Microsoft are still experiencing major problems with their latest update for Windows. The latest spate of issues began last month when the October updates for Windows suddenly began deleting files. The problems also rendered some third-party apps useless. Despite loads of complaints, the company says it's not responsible for how its updates affect third-party apps which worked perfectly before the updates rolled out. And that attitude hasn't eased the anger of many Microsoft customers who are now vowing to divest themselves of the troublesome operating system. To find out more, we're joined by Alex Zaharov-Reut from IT Wire.
The most recent Windows update actually started deleting people's files, so their document folders, and
that was the October one.
even from the cloud. Yeah. And, Microsoft has since fixed that, but then the fix had a problem with zip files where unzipping a zip file could also, in certain circumstances, delete files. And look, Microsoft got rid of a lot of its internal testers, and they tried to use the wisdom of the crowd, as it were, to try and do their testing for them and Windows insiders that sign up to get newer versions of Windows before everybody else. But that is not proper testing.
That's not proper R&D or testing.
Testing, yeah. And this testing is crucial with so many of the world's computers using Windows and with so many programs out there. I mean, making a change that can break different apps, whether it's deleting files or in your case, deleting some of the apps you use to create the shows that you're famous for. Well, I mean, that's a terrible thing. And that's why so many companies don't want to update immediately. That's why a lot of people don't want to update straight away to the latest versions of the Windows, whatever it might be. They'd like to wait and let other people be the beta testers first. And, there's that old saying that says don't buy version 1 of anything. And these days, version 1 can be the latest update to a 30-year-old operating system. That sort of takes you back to version 1 because it's version 1 of some new system.
So how do you opt out?
Well, the problem is with one way is to keep running Windows 7. Because that is something that is Microsoft no longer updating.
A lot of us have Windows 10 already, so how do you opt out of those automatic updates?
Well, you can't. I mean, that's the problem. Ultimately, those updates will be installed. It is possible to say that you're on a metered connection. It is possible to only ask for updates to be installed at certain times of the day, but you can't permanently pause updates in the way that you used to be able to in the past, because ultimately running an out-of-date operating system is a bad idea. People find zero-day vulnerabilities or other issues. One thing you can do in Windows is you can roll back an update. You can go back. And also, I mean, normally you're still given some sort of a choice. I mean, look, I don't run Windows 10 as my primary operating system. I'm running the Mac OS. I actually gave up on Windows back in 2011 because I was sick and tired of all of these sorts of issues.
Yeah, I've decided that my next computer will be a Mac as well. No more Microsoft Windows-based computers because of these update issues.
And look, if you updated the latest version of Mac to Mac OS Mojave and you were on the previous High Sierra version, there were things, including Apple's own spin-off company, ClarisWorks, or FileMaker, basically. I'm sure they haven't called themselves ClarisWorks for years, but FileMaker. FileMaker Pro 14 from memory, it had major problems with macOS Mojave. Now, I'm assuming that those problems have been fixed, but it doesn't matter which system you go with. You need to, if you rely upon those sorts of things, you need to make backups of everything on a regular basis. You need to delay updates until, at least a week or two to see if other people have been affected.
And that report by Alex Zaharov-Reutt from IT Wire. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favorite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.